The universe is bigger than you think. When Galileo first looked at the sky through a telescope in 1609, one of the first things he noticed was that there were far more stars than those visible to the naked eye. Today that might seem obvious, but think about it. No human being before him had ever seen those stars. It was as if the telescope had given him superpowers. This simple observation by Galileo had an extraordinary consequence. It meant that there were stars in the universe farther away than those visible to the naked eye, and therefore the universe was much larger than anyone had imagined up to that point. It also meant that by enhancing our vision with ever more powerful instruments, we could continue discovering new things that had never been seen before, and above all, look ever farther into space. But how big is the universe, and how far can we see? It took a long time to answer these questions, and the answer is a bit more complicated than one might think a little over a century ago. In 1920, at the National Academy of Sciences in Washington, a public meeting was held where two prominent astronomers of the time, Harlow Shapley and Herbert Curtis, were to discuss a problem that was not yet well understood. The meeting was called The Scale of the Universe, but it went down in the history of astronomy simply as the Great Debate. Essentially, Shapley and Curtis had been chosen by the organizers to present the state of knowledge about the size of the universe, each representing a different point of view. According to Shapley, the universe essentially coincided with our own galaxy, the Milky Way. Outside the Milky Way, there was nothing but empty space. Therefore, all the stars and objects observed by telescopes had to belong to our galaxy Curtis. On the other hand, and those who agreed with him, believed the universe was much larger. There were many other objects beyond our Milky Way. Today we know that Curtis was right, but at the time, things were less clear-cut, and it was difficult to determine a definite winner based on the available data. The problem is that measuring distances in astronomy is one of the most complicated things imaginable. Objects are far away. We can't go there. We can't just stretch a measuring tape from here to there, so we must find indirect ways to measure distances. Shapley was an expert in a technique for measuring distances that had been discovered by an astronomer named Henrietta Leavitt. Her method was based on the use of certain stars called Cepheids using Cepheids. Shapley obtained a new measurement of the size of the Milky Way that was very close to the value we know today and consider correct. And he was also the first to realize that the Sun is not located at the center of the Milky Way, but rather in a peripheral position within the galaxy. In short, Shapley was certainly right about some things. Curtis, for his part, like many astronomers of the time, continued to believe that the Sun was at or near the center of the Milky Way, and argued for a smaller size of our galaxy. On these 2 points, we now know he was wrong, but he was right about something far more important. At the time, with the most powerful telescopes available, astronomers could see small patches of light that were clearly not stars, though their nature was not well understood. These objects were called spiral nebulae because they looked like tiny flattened clouds. Shapley and other astronomers believed they were clouds of gas and dust within our own galaxy. Curtis, however, was convinced that they were other galaxies beyond our own, collections of hundreds of billions of stars, like the Milky Way itself, but so far away that they appeared as small, blurry patches in telescopes. The idea seemed almost unbelievable. For these galaxies to appear so small, they would have to be incredibly distant, much farther than seemed plausible at the time. 4 years after the debate, another astronomer, Edwin Hubble, measured for the first time the distance to one of these spiral nebulae, known as M31 in the constellation Andromeda. To do so, he used the very same technique in which Shapley excelled: the observation of a Cepheid variable star within that nebula. The distance Hubble calculated was enormous. M31 could not possibly be part of our galaxy. It was an external galaxy, the one we now commonly call the Andromeda Galaxy. This discovery proved Curtis right, and confirmed that the universe did not end with the Milky Way. Hubble wrote a letter to Shapley to share his discovery. After reading it, Shapley reportedly remarked, "This is the letter that destroyed my universe." Today, we know that the Andromeda Galaxy is about 2.5 million light-years away from us. In other words, the light reaching us from its stars has traveled through the universe for 2.5 million years. It's quite incredible, not only that the light has traveled so far, but also that our telescopes today can capture such detailed images of an object that, just a century ago, appeared as a tiny blurry spot, even in the best instruments. But an even more astonishing realization of the past century is that Andromeda is merely the closest spiral galaxy to us, and that the universe contains hundreds of billions of other galaxies, many even farther away. In every direction we look, there is an immense number of galaxies, meaning the universe is unimaginably larger than anyone once thought. But just how big is the universe? With the increasingly powerful instruments we've built, we've been able to look farther and farther out into space. But as we've said, the light that reaches us from distant parts of the universe takes a very long time to get here. So when we look far into the universe, we're actually seeing a younger universe. Another thing we've learned over the past century is that our universe has existed for about 13.8 billion years. So of course, we can't look so far as to see objects older than that. The oldest thing we can observe in the universe is the hot matter that filled space in the very early stages of its history. In fact, we have managed to see it, or rather, to see the light emitted by that matter about 400,000 years after the universe began. It's called the cosmic microwave background radiation. It comes from every direction in space and is the best evidence we have that the universe was once very different from what we see today, and that there really was something we call the Big Bang. But the most distant galaxies we can observe are so far away that their light has traveled for almost the entire history of the universe. The farthest one ever observed appears as it was only 300 million years after the Big Bang. The James Webb Space Telescope was designed precisely to push that limit even further, to look deeper and find galaxies even more distant. But as I said, we'll never be able to see beyond the cosmic microwave background. So, the size of the observable universe is defined by the distance light has traveled since it first began its journey, about 13.8 billion years. But here's where confusion often arises, one of those questions that seems impossible to settle. If the farthest light we can see started its journey 13.8 billion years ago, does that mean the radius of the universe is 13.8 billion light years? Actually, no. The observable universe is much larger than that. Its radius, the distance to the edge of the region we can observe, is about 46 billion light years. Why? The answer is simpler than it seems. The fact is, the universe is expanding. If the universe were static, that is, if space itself weren't expanding, then indeed, the farthest points we could see would be about 13.8 billion light years away. The light emitted just after the Big Bang would reach us 13.8 billion years later, after traveling 13.8 billion light years. In that case, the universe would have a radius of 13.8 billion light years. Simple. But the universe isn't static. Space itself is expanding. So, while the light from a distant point was traveling toward us, that point itself was moving farther away. As a result, today it's at a much greater distance than when the light first set out. When we take this expansion into account, we find that the region we can observe today has a radius of 46 billion light years, not 13.8 billion, as one might naively think. But why exactly 46 billion light years? Well, to answer that, you have to do the math using general relativity and know the parameters that describe the universe, such as how much matter it contains, how fast it's expanding, and so on. When we run those calculations, that's the result: 46 billion light years. In short, the observable universe is truly enormous, and in fact, it's even larger than it might seem at first glance. Of course, space doesn't end. It has no edge. It continues far beyond the region we can observe. We simply can't see any farther. But if you think about it, what we've managed to achieve is truly incredible. In just over 4 centuries, we've gone from a simple telescope pointed at the sky to observing the very edges of the visible universe. Every time we think we've found a limit, we discover that it's actually just the beginning of something even greater. So perhaps the real question isn't how big the universe is, but how far we're willing to go to explore it. And if you too want to keep exploring with us the most fascinating questions about the universe, subscribe to the channel and turn on the notification bell, because the next discovery could once again change everything we think we know.